Hey, hi everyone, welcome back to my YouTube channel. So, today we will be discussing a question that has been taken from rotational kinematics. Now, before getting started with this question, I would like you to know two concepts which are pretty important for understanding this question. First is the law of conservation of energy, and second is no slipping condition. Now, what does the law of conservation of energy says? That energy can neither be created nor be destroyed, but it can only be transferred from one form to another. Whereas no slipping condition says that V is equals to capital R omega. V being your linear velocity and R being the rotational velocity. And R is the radius. So here in this question we have taken a disk whose mass is capital M, radius is capital R, and it is rolling down an inclined plane of height h without slipping. We have to figure out the speed of the disk at the bottom of the incline, and the acceleration of the gravity given to us is g, and the moment of inertia of disk is half capital M capital R square. Now let's have a visual representation of this question. So we'll draw kind of an inclined plane, kind of look like, okay, good to go. So it is at a height of h above the ground. Now here we will be taking a rotational disk. Let's say the radius is capital R and it is rolling down. Now, when it is rolling down, it is under two kinds of motion, rotational as well as translational. Now, we have to figure out what is the speed of this disk at the bottom of the inclined plane. That means when it reaches over here. So now when it has reached over here, now the ball is no longer rotating, it's only translating. So we will be concerned only with the linear velocity. Now according to the law of conservation of energy, what is applied over here? That loss in the gravitational potential energy is equal to gain in translational kinetic energy plus gain in rotational kinetic energy. Why it is said so? Now see, when the disk was at the top position of the inclined plane, it was at a height of h from the ground level. When it is descending down, the height from the ground level is further decreasing, right? So that means there would be a loss in the potential energy possessed by the disk. Now that loss is covered up by the gain in translational as well as rotational kinetic energy. So I would represent the gravitational potential energy as capital mgh, translational energy as half capital mv square, and rotational kinetic energy as half I omega square. Now according to the question, the value of I given to us is half mr square. So we're gonna plug in the value. So this becomes mgh is half mv square, half into half capital mr square omega square. Now we also know that according to the no slipping condition, V is equal to R omega, or V by capital R is equal to omega. So we're going to replace the omega value with V by R. So now my new equation becomes mv square plus 1 over 4 capital M R square V square over R square. These two got cancelled. Now the equation is mgh half mv square 1 by 4 m v square again. We're going to cancel up the m and simplify it. So the equation is now left with 3 by 4 v square. which can also be written as 4 over 3 GHs V square, or the value of V is square root 4 by 3 GH. Now this is the speed of the disk when it is at the bottom of the inclined plane. So according to the question, option 4 is absolutely correct. Root under 4 by 3 GH. This is the speed at which the disk is moving at the bottom of the inclined plane. So I hope this solution would be helpful for a lot of students who are practicing this topic, and I'll make sure I'll come up more of these questions often. So do subscribe to the channel, like the video, and yeah, thank you.